Let's do a problem involving tangent lines and implicit differentiation. So this problem is actually going to be a little bit tricky and involved. It's a really good example that shows a lot of different steps. So here are the directions. Find all points with horizontal tangent lines on the curve x to the fourth minus x squared y plus y to the fourth equals 1. Okay, so we're going to be dealing with implicit differentiation here. This is not a function. If you were to look at its graph, which I actually have right here, this is its graph. It does not pass the vertical line test. So we need to use implicit differentiation to find the derivative. So we do want to start by finding the derivative, since we're going to be asking ourselves questions about the tangent lines. So let's go ahead and do that. Let's find the derivative of this curve. Okay, so I'm going to start by taking the derivative of both sides with respect to x. Okay, so left-hand side. So the derivative of x to the fourth is just 4x cubed minus, okay, so here we have x squared times y, so I'm going to need to use the product rule on that piece there. So it's going to be the first times the derivative of the second, and I'm just going to leave it written like this for a step, plus the second, which is y, times the derivative of the first, x squared. Okay, so that was just all the product rule for the term x squared y. But now I have plus y to the fourth. So I need to take the derivative of that. I'm going to start by using the power rule to bring that 4 down, so 4y cubed. But now, since we're using implicit differentiation, we're thinking of y as a function of x. So I need to multiply by the derivative of y here, which is dy dx. So that's a chain rule in action, and you always need to remember that when you're doing implicit differentiation. Okay, so 4y cubed times dy dx equals the derivative of 1, which is 0. Okay, so let's work inside this parentheses here. So 4x cubed minus, so I've got x squared times the derivative of y, so that's dy dx, plus y times the derivative of x squared, which is 2x. Okay, and then out here we still have plus 4y cubed dy dx equals 0. Okay, last of all, I'm going to distribute the subtraction sign to both terms within the parentheses. So that's going to give me 4x cubed minus x squared dy dx minus 2xy plus 4y cubed dy dx equals 0. Okay, now we finished actually taking the derivative, but we need to solve for dy dx to complete the process. So to solve for dy dx, the general strategy is to collect all the terms with the dy dx on one side and all the terms without on the other side of the equal sign. So if I do that in this case, I'm going to have 4y cubed dy dx minus x squared dy dx on the left-hand side equals, and then all my terms without on the other side. So that's going to give me a 2xy minus 4x cubed on the right-hand side. Now on the left-hand side, I can now factor out a dy dx from both terms. 4y cubed minus x squared left over equals 2xy minus 4x cubed. And then to complete the process of finding the derivative, I'm going to divide by this factor in parentheses and get dy dx equals 2xy minus 4x cubed over 4y cubed minus x squared. Okay, so this is the part that you've probably seen before. Hopefully it's a little bit familiar. So far we've simply found the derivative using implicit differentiation. But now comes the part that's a little more complicated. We want to find all points with horizontal tangent lines. So remember what the graph looked like. So it's kind of this, it's a closed shape. It's not a circle or an ellipse, but it is closed. So you can imagine that there's going to be multiple points on here that have horizontal tangent lines. So we want to find all of those points. So how do we do that? Okay, so what do we know about horizontal tangent lines? Horizontal tangent lines occur when the slope of the tangent line equals 0. Okay, so let me just write that down really quick. So horizontal tangent lines occur when the slope of the tangent line equals 0. Okay, and we have the slope of the tangent line. The derivative is the slope of the tangent line. So essentially what we need to do is we need to find the points where the derivative equals 0. So we want to find the points where dy dx equals 0. Now when we actually do this, the process is going to be kind of tedious. The algebra is tricky. But throughout all of this, if you get lost in the algebra, I just want you to remember the overall concept of what we're doing. We're trying to find the horizontal tangent lines, and that means we're trying to find the points where dy dx equals 0. So always just come back to that concept if you get lost in the details. Okay, so let's go about actually doing that. So we want dy dx, which is 2xy minus 4x cubed over 4y cubed minus x squared. We want that to equal to 0. Now this is a little bit trickier than what we did maybe back in the beginning of learning derivatives because it's a rational function, it's a fraction. So remember that a fraction equals 0 when its numerator equals 0. We don't want the denominator to equal 0 here, right? Because that gives us something undefined, which isn't what we're looking for. We're just looking for this fraction to equal 0. And that happens when the numerator equals 0. So then what we're actually looking to find is where 2xy minus 4x cubed equals 0. Okay, well that simplifies things a little bit at least. So let's solve this. Each of these terms has an x, so I can factor out that x. And if I do that, I get x times 2y minus 4x squared equals 0. Okay, now we have two pieces being multiplied together, and this equals 0. So we know that this can be true when either of the pieces individually equals 0. So we can have x equals 0, and this relationship would be true. Or we could have 2y minus 4x squared equals 0, and this relationship be true. So both of these scenarios are going to give me horizontal tangent lines. So both give horizontal tangent lines. One of these is a little easier to think about, and that's of course x equals 0. That's a lot simpler, right? So let's start with that. Remember that we're looking for the points with horizontal tangent lines. Right now we just know that there's a horizontal tangent line when x equals 0. So how would we go about finding the y values that are associated with x equals 0? Well, we simply go back to the original relationship, the original curve. So remember we had x to the fourth minus x squared y plus y to the fourth equals 1. So let me write that back down here. So my original equation was x to the fourth minus x squared y plus y to the fourth equals 1. We know there's a horizontal tangent line whenever x equals 0. So to find the y value that goes along with that, I'm going to simply plug in x equals 0 to this original equation and solve for y. Okay, so if I do that, I get 0 to the 4th minus 0 squared y plus y to the 4th equals 1, which just gives me y to the 4th equals 1. Now this is going to be true when y equals positive or negative 1. Taking the 4th root is like taking the square root. You need to put that plus or minus in there. Okay, so we found out that there are horizontal tangent lines at 2 points, 0, 1, and 0, negative 1. So this is part of our answer. Now let's just go over to the graph and see if that makes sense. So I'm just going to graph on top of this the line y equals 1. And then also y equals negative 1. Oops, sorry about that. That should be y equals negative 1. And okay. So we can see that these indeed do look like tangent lines to the graph at the respective points, right? At this point 0, 1, and this point 0, negative 1. Okay, so we found two horizontal tangent lines, 2 points with horizontal tangent lines so far, but we know that there's more work we have to do because so far we've only dealt with this piece of information. But we still need to deal with the fact that they are horizontal tangent lines when 2y minus 4x squared equals 0. So let's just devote a whole section to that. That's going to be kind of the more challenging part of our adventure here. Okay, so let's kind of start a new section here. So what do we have? We have the relationship 2y minus 4x squared equals 0. Okay, we know there are horizontal tangent lines when this is true. But let's make this a little simpler by solving for y in this relationship. Okay, so I can move the 4x squared over there like that, and then I can solve for y and actually get y equals 2x squared. So I know that there are horizontal tangent lines when y equals 2x squared. And y equals 2x squared is the equation of a parabola. And actually, let me go back to my graph here while I talk about this. I can graph y equals 2x squared on here. But I'm really only interested in the places where y equals squared hits my curve, right? My implicit curve. So here and here, those points C and D that I just created, those are where my horizontal tangent lines are going to occur. So I need to somehow figure out what those points are from this equation of the parabola that passes through them, if that makes sense. Okay, so let's go back to the board here. Okay, so what am I going to do here? I know horizontal tangent lines happen when y equals 2x squared. So once again, I'm going to go back to my original equation. Okay, so my original equation was x to the 4th minus x squared y plus y to the 4th equals 1. So if I plug in y equals 2x squared to this original equation, then I can solve for the x values, right? So I'm kind of eliminating a variable. I know the horizontal tangent lines happen when y equals 2x squared, but I've got kind of too much information, so I'm going to eliminate a variable by plugging this into here and then solving for x. Okay, so let me show you what that's going to look like. X to the 4th minus x squared, and then I'm going to plug in y equals 2x squared. So y equals 2x squared plus 2x squared to the 4th equals 1. All right, so this is going to be x to the 4th minus 2x to the 4th plus. Now be careful, you're raising the entire quantity 2x squared to the 4th power. So I need to raise 2 to the 4th power, which is 16. And then x squared to the 4th power. When you have a power raised to a power, you multiply them. So that's x to the 8th equals 1. So this is 16x to the 8th minus x to the 4th equals 1. And I'm going to move everything to one side and get 16x to the 8th minus x to the 4th minus 1 equals 0. Now, if I can just solve this equation for x, I would know the x values where there were horizontal tangent lines. And then from there, I could, of course, find the y values. But solving this equation is kind of the tricky thing. So it may have looked like we were making progress, but actually we were kind of falling deeper into this rabbit hole of algebra. So I just want to give you a warning here. This is going to get a little tricky. But I do want to show you this example because I think it's good to see a few complicated examples every once in a while. But if the algebra is too confusing for you, that's okay. This is probably a little harder than what you'll see on a test. Just keep in mind what we're trying to do overall. We're just trying to find the places where the derivative equals 0. And in this case, that requires some tricky algebra. But I'll try and help you out here with the steps. Okay, so we're trying to solve this equation for x. That's all we're trying to do right now. And sorry, they're doing construction here, so if you hear any loud noises, that's just construction. So this almost sort of looks like a quadratic, right? Except instead of having a squared term and just an x, I have a term to the 8th and a term to the 4th. But besides that, it almost looks like a quadratic. So I'm going to take advantage of that and make a little bit of a substitution here. So I'm going to let z equal x to the 4th. Okay, so just go with me here, and I think you'll see why this works. So now let me rewrite this with my substitution. So then this becomes 16z squared, right? If z is x to the 4th, then 16x to the 8th would be 16z squared minus z minus 1 equals 0. Okay, and let me kind of put this out to the side. So you remember, we're just doing a substitution kind of to help us solve this problem. Okay, now this we can solve, right? We might not be able to factor it, but we can at least use a quadratic equation to solve this quadratic equation. Okay, so that's what I'm going to do now. I'm going to find the solutions. So z equals by the quadratic formula. If you remember, opposite of b, plus or minus the square root, all of that. So it's going to be opposite of -1. So 1 plus or minus the square root of b squared. So -1 squared minus 4ac. That's 4 times 16 times -1. All over 2a. Okay, and then we do a little simplification. So that's 1 plus or minus, if you work all that out under the square root, it's 64, or sorry, 1 plus 64, or 65, over 32. Okay, so now we have a solution in z, but remember we had made that little substitution where we let z equal x to the 4th. So if we want to go back to our original variable, x, let me make some room here. So if z equals x to the 4th, then x, if I solve for x, is plus or minus the 4th root of z. Okay, so I just solve for x by taking the 4th root of both sides, but since it's an even root, I have to do the plus or minus thing. So then, my solutions in x are x equals, okay, so I'm going to write them as two separate. So plus or minus 1 plus root 65 over 32. And plus or minus 1 minus root 65 over 32. Okay, so there's 4 possible x values here that would give us the horizontal tangent lines. let's back up a step though, because 1 minus this root here, 1 minus root 65 is negative. So I can't take the fourth root, and sorry, these should both be fourth roots. I can't take the fourth root of a negative number, just like I can't take the fourth root of, or the square root of a negative number. So this is actually not an option. So what we're left with really is just plus or minus the fourth root of this 1 plus root 65 over 32. Okay, so essentially all I did in that step is I had this 16x to the 8th minus x to the 4th minus 1 equals 0 I was trying to solve. I realized it looked kind of like a quadratic, sort of, so I made a substitution that actually did make it into a quadratic. I used the quadratic equation to solve it, and then I went back to my original variable, which was x, by taking the fourth root of z. Okay, so that's kind of the messy algebra I was talking about. So don't let that bog you down too much. But now what do we have? We actually have the x values where there's a horizontal tangent line. So x values for horizontal tangent lines. So now there's only one other small step to do. I just need to find the y values that go with those x values. So how do I do that? Well, remember what we started with. We knew that horizontal tangent lines happened when y equals 2x squared. So all I need to do is plug in my x values to that. So if y equals 2x squared, then y equals 2 times, and I'm going to write this all out, but then we'll reduce it. Just this x value we got, plus or minus the fourth root of 1 plus root 65 over 32 squared. Now, whether that what's inside the parentheses is positive or negative, when I square it, I'm still going to get the same positive value. So this is really 2. Okay, and when I square a fourth root, I get a square root. So this is just 2 square root of 1 plus root 65 over 32. So I see that, so I had two x values, right? Plus or minus this quantity, but they each had the same y value since I'm squaring the x. So now I can finally write down my two other horizontal tangent line points. So horizontal tangents at, so we have positive fourth root of 1 plus root 65 over 32 and the associated y value, which is 2 square root of 1 plus root 65 over 32. And then the same point, but with a negative x value. So negative fourth root, 1 plus root 65 over 32. And then the same y value here. Okay, and just so this is a little bit easier to graph, if you were to approximate these, this would be 0.7295, 1.0643, and then negative 0.7295, 1.0643. Okay, so we found two more horizontal tangent lines. So if I quickly go back to our graph here, let me just graph that. They both have the same y value, right? This 1.0643. So let's look and see where that is on the on here. And that makes sense, right? That kind of looks like where we expected it to be. So my tangent lines are at the points 0.7295, 1.0643, and then negative 0.7295, 1.0643. And that looks about right if we look at the graph. All right, so once again, remember the overarching concept here. We use implicit differentiation to find the derivative, and then we wanted to find the horizontal tangent lines. So to do that, we set it equal to 0, which amounted to set the numerator equal to 0. And then there were these different possibilities we had to deal with, but we ended up with 4 points where there were horizontal tangent lines.